What if I told you that companies like Google and Amazon reject thousands of candidates who can't solve a simple array problem that has a secret one-line solution? And what if I told you that by the end of this video you will know a technique so powerful that it will transform any range sum problem from minutes of computation to microseconds? Stay till the end because I will also reveal the exact interview question that Amazon asked last month that stumped 80% of candidates. But after watching this video, you will solve it under 30 seconds. This technique is called Prefix Sum and it's about to become your secret weapon. Hello world class coder, welcome to BackToCoding. I am Milind Amrutkar and today we'll break down Prefix Sum, the technique that separates amateur coders from professional developers. But before we dive in, if you are serious about cracking those technical interviews, hit that subscribe button and ring the notification bell because what you are about to learn is pure gold. Let me start with a story. Imagine you are a marathon runner and every kilometer someone asks you how far have you run so far. Now you have two choices, either count every step from the beginning each time someone asks or simply remember your cumulative distance at each kilometer marker. Which would you choose? Obviously the second one. That's exactly what Prefix Sum does in programming. Let me show you what I mean with actual numbers. Imagine we have a fitness tracker that records calories burned each hour, 100, 150, 200, 120, 180. These are calories burned in hours 1, 2, 3, 4 and 5. Now if someone asks total calories burned by hour 3, without Prefix Sum we calculate 100 plus 150 plus 200 which is 450. But what if we pre-calculate cumulative totals? We create what's called a prefix sum array. 100, 250, 450, 570, 750. Let me show you how we built this. Hour 1 is 100 calories, just the first value. Hour 2 is 100 plus 150 which is 250 total calories. Hour 3 is 250 plus 200 which is 450 total calories. Hour 4 is 450 plus 120 which is 570 total calories. Hour 5 is 570 plus 180 which is 750 total calories. Now here's where the magic happens. What if someone asks how many calories were burned between hour 2 and hour 4? Without Prefix Sum, we would add 150 plus 200 plus 120 which is 470 calories. With Prefix Sum, we take Prefix Sum of 4 minus Prefix Sum of 1 which is 570 minus 100 which is 470 calories. One subtraction instead of 3 additions. Think about this like looking at your car's odometer. If you want to know how far you drove on a trip, you don't count every mile marker. You just subtract the starting reading from the ending reading. Let's quickly revise. Prefix Sum is just cumulative totals stored at each position. It's like keeping a running score where each position tells you the total from the beginning up to that point. And the superpower? Any range sum becomes just one subtraction. Simple, right? Now let's see this in action with a real coding problem. Here's our challenge. You are building a financial dashboard for a startup. They have daily revenue data for 10 days and they need to quickly answer questions like what's our total revenue from day 3 to day 7. They will ask hundreds of these questions, so speed matters. In the challenge, we have daily revenues like 1000, 1500 and so on. And we are given some queries to answer like total revenue from day 3 to day 7 or total revenue from day 1 to day 5 and so on. And the expected output are like for query 1 it will be $7,200 which is 800 plus 2000 plus 1200 plus 1800 plus 2200. For query 2 it will be $6,500 which is 1000 plus 1500 plus 800 plus 2000 plus 1200. Let's solve this both ways, brute force and with Prefix Sum, so you can see the incredible difference. Here's the complete solution. Don't worry, we will dissect every single line together. Alright, let's break down this code line by line so you understand every single detail. Starting at the top, we have our main class Prefix Sum master class. Inside main, we initialize our daily revenue array with 10 days of revenue data. Now let's focus on the heart of our solution, the build Prefix Sum with explanation method. Here we get the array length and create a new array called Prefix Sum of the same size. This will store our running totals. the first element of prefix sum is always identical to the first element of the original array. Why? Because there's nothing before it to add. So prefix sum of 0 is array of 0, which is 1000. This is where the magic happens. We loop from index 1 to the end. For each position I, we calculate prefix sum of I, which is prefix sum of I minus 1 plus array of I. Let me trace through this. At I equals 1, prefix sum of 1 equals prefix sum of 0 plus array of 1, which is 1000 plus 1500, which is nothing but 2500. At I equals to 2, prefix sum of 2 is prefix sum of 1 plus array of 2, which is nothing but 2500 plus 800, which is 3300. At I equals 3, prefix sum of 3 is prefix sum of 2 plus array of 3, which is 3300 plus 2000, which is nothing but 5300. See the pattern? Each position builds on the previous one, creating a cumulative sum. Now let's look at our two calculation methods. Brute force method. This is the naive approach. Look at calculate range sum brute force method. We literally loop through every element from left to right and add them up. If your range has 1000 elements, you do 1000 additions every single time for every query. Optimized prefix sum method. This is where we see the power. Look at calculate range sum optimized method. If the range sum starts at index 0, we just return prefix sum of right. Why? Because prefix sum of right always contains the sum from 0 to right. And for any other range, we use the formula prefix sum of right minus prefix sum of left minus 1. Let me explain this with an analogy. Imagine you are tracking your steps on a fitness tracker. At 2 pm, you have walked 5000 total steps. At 5 pm, you have walked 12,000 total steps. How many steps between 2 pm and 5 pm? 12,000 minus 5,000. It's 7,000 steps. That's exactly what we are doing here. Prefix sum of right gives us the total from start to right. Prefix sum of left minus 1 gives us the total from start to just before left. Subtract them and we get the sum of just the range we want. When you run this program, here's exactly what you will see. I want you to visualize this as if we are at a whiteboard. Our original array is 1000, 1500, 800, 2000 and so on. For building the prefix sum array, let's start with index 0. Prefix sum of 0 is 1000. This is just the first day's revenue. Move to index 1, we take the previous sum 1000 and add today's revenue 1500. So prefix sum of 1 is 1000 plus 1500, which is 2500. This represents total revenue from day 1 to day 2. Index 2, prefix sum of 2, 2500 plus 800, which is 3300. Total from day 1 to day 3. Index 3, prefix sum of 3, which is 3300 plus 2000, which is nothing but 5300. Total from day 1 to day 4. Continue this pattern all the way to index 9. Prefix sum of 9 is 13,000 plus 1900, which is 14,900. Our complete prefix sum array is 1000, 2500, 3300, 5300, 6500 and so on up to 14,900. Now let's answer our queries which were asked in the problem statement. Let's process our first query, which was for total revenue from day 3 to day 7. Days 3 to 7 correspond to indices 2 to 6. Remember, arrays are 0 indexed. Using brute force, we would add array of 2 plus array of 3 plus array of 4 plus array of 5 plus array of 6, which is 800 plus 2000 plus 1200 plus 1800 plus 2200, which is 7200. Now using prefix sum, we calculate prefix sum of 6 minus prefix sum of 1, which is 10,500 minus 2,500, which is nothing but 7,200. Why does this work? Think about it. Prefix sum of 6 contains the sum from day 1 to day 7, which is 10,500. But we don't want days 1 and 2. Prefix sum of 1 contains the sum of days 1 and 2, which is 2,500. When we subtract, we remove exactly what we don't want. Let's process query 2. Total revenue from day 1 to day 5. Days 1 to 5 correspond to indices 0 to 4. Since we are starting from index 0, we simply take prefix sum of 4, which is 6500. No subtraction needed. Let's verify. 1000 plus 1500 plus 800 plus 2000 plus 1200, which is 6500. Perfect. So the pattern here is for range of left comma right, answer is prefix sum of right minus prefix sum of left minus 1. Special case when left is 0, answer is prefix sum of right. Quick recap before we analyze complexity. We built a prefix sum array where each element stores the cumulative sum from the start. Any range sum query becomes a simple subtraction. Prefix sum of end minus prefix sum of start minus 1. We have transformed an O of n operation into O of 1. That's the power of pre-processing. Ready for the complexity analysis? Let's go. Let me break down the complexity analysis in detail because this is crucial for interviews. Time complexity analysis. First, let's talk about the brute force approach. For each query, we loop through all the elements in the range. If the range has k elements, that's O of k time. In the worst case, k would be n, the entire array. So it's O of n per query. If we have q queries, total time complexity is O of q times n. Example, if you have an array of 10,000 elements and 10,000 queries, that's potentially 100 million operations. Now the prefix sum approach. Building the prefix sum array, we visit each element exactly once, so O of n. Each query after that, just one subtraction regardless of range size, so O of 1. For q queries, O of n plus q, total time. Using our same example, 10,000 elements and 10,000 queries, only 20,000 operations. That's 5,000 times faster. Think about this. As the number of queries increases, the initial O of n pre-processing cost becomes negligible. If you have a million queries, the difference is even more dramatic. Space complexity analysis, brute force, uses O of 1 extra space. We only need a variable to accumulate the sum. Prefix sum uses O of n extra space for the prefix sum array. This is a classic space-time trade-off. We are using extra memory to store pre-computed values, which dramatically speeds up our queries. In modern computing, where memory is relatively cheap but time is expensive, this trade-off almost always makes sense. Important interview point. If someone asks, can we reduce the space complexity? The answer is yes, if you don't mind sacrificing query speed. We could compute sums on demand without storing the prefix array, but then we are back to O of n per query. Let me share real-world applications where prefix sum is actually used in production. Financial systems. Banks use this for calculating running balances. Every transaction in your bank statement shows a balance. That's prefix sum. When you check your balance at any point, it's O of 1 lookup. Stock trading platforms. Calculating moving averages, cumulative volume, and running profit loss. Robinhood and E-Trade use variations of this technique. Social media analytics. When Instagram shows cumulative likes over time or Twitter shows tweet impressions, they are using prefix sums to quickly generate those graphs. Cloud computing billing. AWS and cloud computing calculate your cumulative usage and costs using prefix sum techniques. When you ask, what's my bill from March 15 to March 28, that's a range query. GPS and maps. When Google Maps calculates the distance for part of your route, it uses prefix sums of segment distances. Now let me give you the exact interview questions and answers that will make you stand out. When should you not use prefix sum? Prefix sum is not ideal when first the array is frequently updated and we would need to rebuild the prefix array each time, making updates O of n. For dynamic arrays, I would use a Fenwick tree or segment tree instead. Second, when we only have one or two queries, The pre-processing overhead isn't worth it. 3. When memory is extremely limited and we can't afford O of n extra space. Can you optimize prefix sum for very large arrays that don't fit in memory? Yes, we can use a technique called chunking or blocking. Divide the array into chunks that fit in memory. Maintain a prefix sum for chunk totals and detailed prefix sums within each chunk. This gives us a two-level prefix sum structure. Query time becomes O of root n with O of root n memory if we choose optimal chunk size. How would you handle overflow for very large numbers? 3 strategies. First, use long instead of int in Java for 64-bit integers. For even larger numbers, use big integer for arbitrary precision, though with performance cost. Third, if you only need modular arithmetic, we can store all values modulo some prime number, which prevents overflow while maintaining correctness for modular queries. Can prefix sum work with other operations besides addition? Absolutely. The technique works with any associative operation. Prefix product for multiplication, prefix XOR for bitwise operations, prefix min-max for range minimum maximum queries. The key requirement is associativity. The operation must satisfy this. Alright, remember I promised to reveal that Amazon question that stumped 80% of candidates last month. Here it is. Given an array of integers and an integer k, find the total number of continuous subarrays whose sum equals exactly k. This is lead code 560. Subarray sum equals k. Most candidates try nested loops, giving O of n square. But watch this. Why this stumps candidates? They don't recognize it's a prefix sum problem. They try brute force with nested loops. They don't think of using a hash map to track previous sums. The key insight here is, if current prefix sum minus k is previous prefix sum, then the sub array between them sums to k. We use a hash map to count how many times each prefix sum occurs, solving it in O of n time and space. This single question tests prefix sum, hash maps and mathematical reasoning. Master this pattern and you will ace similar problems. If this video helped you understand prefix sum, smash that like button. It really helps the YouTube algorithm share this with other aspiring programmers. Subscribe and hit the bell icon so you don't miss our next video. And comment below what DSA topic should I cover next. I read every single comment. Until next time, keep coding like the champion you already are and keep watching Back to Coding.